Today I'm going to talk about solubility curves. So here's a little bit of review, stuff we've already done. Remember that you can classify mixtures as heterogeneous or homogeneous. And a mixture is two or more substances. So homogeneous, you can't see the difference. So typically a single phase. In order to make a homogeneous mixture, you have a solvent and a solute. The solute is the thing that gets dissolved, and the solvent is the thing that does the dissolving. When you put your solute solvent together, you get your homogeneous mixture, otherwise known as a solution. So here we've got some cool examples. You're mostly familiar with a solid dissolving into a liquid, sugar and water, salt and water, etc. You can dissolve a solid in a solid, though. If you've got, put them in liquid form, mix them up. Bronze is a common one. That's copper and zinc mixed together, and it makes a stronger metal called an alloy. When you mix metals together, that's called an alloy. Mothballs and the carbon in filters. So if you drink filtered water from a pitcher or fridge, you have solid carbon, and the gases in the water will dissolve in that carbon. So in other words, those gases basically get absorbed by the carbon. They literally dissolve in that solid. That's what gets rid of the basically flavors. It doesn't, unless you got a very sophisticated filter, it's not going to really filter out poisons. Liquid and liquid, so alcohol and water. Soda is where you have a gas dissolved in a liquid, and then the air in the room, the air you're breathing now, is actually a mixture and technically a solution. So okay, that's like 78% nitrogen and 18%, 20% oxygen, and so on. So we also have saturated and unsaturated. Saturated means you have the maximum amount that can dissolve. If you put any more in there, any more solute, more sugar in the water, it's going to settle to the bottom. That's called a precipitate. Unsaturated means less than the max. You can keep putting more in there. Notice that these have something about temperature in the definition, and that's what I'm going to show you today. We've not talked much about supersaturated, but it is possible to dissolve more solute than is possible, which sounds ridiculous for me to say that, but it's true. They're temporary solutions. They're unstable. That's why you don't see them as much. So what you do is you heat up the solvent. So let's do sugar and water. You heat up your water really hot, and you can dissolve a lot more sugar in it. Then you cool the solution down, and then as you're very, very careful with it, you don't bump it or disturb it, that sugar will remain in solution. It'll remain dissolved, even though it's really not supposed to, because there's too much in there. If you disturb it, if you bump it hard, then a lot of the crystals of the sugar will form crystals and fall out of solution. That's a precipitate. Another way to disturb it is provide what's called a nucleation site, where the sugar particles can gather. One or two of them gather on typically a rough surface, and these will cause the other sugar molecules to attach to that, and they attach in the same repeating structure. That's called a crystal. And let's say we've got our supersaturated sugar water. If you introduce a rough surface like a wooden stick, you just put a stick in there, then the sugar will slowly crystallize around the stick, and you've made rock candy. So you're familiar with some of the things that come out of it, but I don't know if you've ever done it for yourself. Another one is those hot packs for medical use. You have this bag of liquid, and there's like a little clicker in there and a little like metallic disc, and you're told to click it, and then all of a sudden it goes solid and gets really, really hot. That is heating it up. It's usually sodium acetate, I think. I can't remember. I think that's what it is. But you supersaturate it. They put it in the bag. They put a little clicker in there, which provides activation energy, is what that's called. And it's like those little toys that you click, and they're completely useless other than they make a little clicking noise. And you click it, and it provides a place for the this quick momentary instance where the sodium acetate can crystallize, and then all the energy it took to dissolve it is released back out in the form of heat. So fairly useful stuff. Okay, that's the background for what is called a solubility curve. A solubility curve is a graph where you put solute on the y-axis and temperature on the x-axis. Solute is typically expressed in grams per 100 grams of solvent, and we're just going to stick to water because it's super easy. So this curve here, and you'll see why it's a curve. Well, you'll see how we plot the data. Why it's a curve is a little strange, but that's just all math. We're not doing it. So if I figure out, I can plot how many grams of, say, sugar per 100 grams of water at some given temperature. Now, if you already kind of know that you can dissolve more solute, more sugar, in warm water. So my graph should be high over here, and as it cools down, I can dissolve less. So lower temperature and less should be something like that. And in fact, this is the type of thing that you would see for water and salt and quite a few things. So what we have is, okay, let me break this down here. We have this line, and what it says, the way that you read it, is 40 grams will dissolve in 90 degrees of water. So I'm just sticking to sugar and water because that's what we know. So if I've got 90 degree water, how much sugar can I put in? 40 grams. It's probably a lot more than that. Well, actually, for sugar, it's about the same. Because remember, it's 40 grams per 100 grams of water. So any point along this line is the saturation point. This is the max that I can, this is the most sugar I can put in here. Okay? So let's see. Let me come down here. Okay. So check this out. We have 90 degrees Celsius, so that's over here. We have 40 grams, okay, we're using salt, 40 grams of sodium chloride, there's our 40 grams, in 100 grams of water represents a saturated solution. Okay, so this is how you would read this sort of graph. But check this one out. At 90 degrees, I've got 30 grams dissolved. Where's my other 10 grams? That other 10 grams is what I can still dissolve. If I can still dissolve something, that is called an unsaturated solution. It's less than the maximum. Remember, the maximum was 40 up there. So in this case, I've got 90 degrees Celsius, 30 grams of sodium chloride per 100 grams of water. So remember, this is like grams of solute per 100 grams of solvent, which in this case is water. And this is saying, hey, I can add 10 more grams to that. So anything on the line is saturated, anything under the line is unsaturated, and you can probably guess what's above the line, and that would be supersaturated. So right here, that 90 degrees, let me do this, that 90 degree water, and I have 50 grams of salt, sodium chloride, is above the line. I have 10 extra grams, so that is supersaturated. Remember, it's unstable. The excess, that 10 grams right here, can easily precipitate, fall down to the bottom, or crystallize, make rock candy, that sort of thing. Okay? So below the line is unsaturated, on the line is saturated, above the line is supersaturated. And the cool thing is, I can make stuff, I can make the same solution, all three of those, by simply changing the temperature. So if I have, let's say, I don't know how many grams this is. Let's just pick something. Looks like 50. I don't know. We'll just call it 50 because why not? Okay, so we have 50 grams of salt, and at whatever temperature this is, I can dissolve 50 grams. But as I cool it down, the salt reaches the saturation point where you can no longer hold any of the salt in solution. So then any further cooling, it becomes supersaturated. So this is something you'd want to, let sit and not disturb. This is explained or demonstrated in a popular, it was a YouTube video a few years back where people up north would leave a bottle of water in their car, and in the morning, and it's like so cold, it'd be like 20 degrees, 0 degrees, below zero, and they would get the bottle of water and it was clearly a liquid, and then they would shake it or take the cap off or something, and it would instantly freeze, which is kind of cool. It's basically the water crystallizing out of solution there, but it's one of those, and I cannot remember what solution it is. I don't remember if they had to put a little something in it ahead of time, to cheat a little bit, or if it had to be an unopened bottle. But it explains a lot. So temperature is one of the main things that tells you how much can dissolve. Now keep in mind, it's not just increasing the temperature. If you leave soda out on the counter and it warms up, it goes flat. The flat means that there's less carbon dioxide dissolved in it. If you dissolve a gas in a liquid, it's the opposite of doing solid in a liquid. The hotter the gas, the less gets dissolved. The colder, the more is dissolved. What's the best way to enjoy a soda? Ice cold, because it's got more of that carbonation in it. Okay? You've seen, I know that you've watched The Simpsons, and they have these giant cooling towers at the nuclear power plant. What's going on there is any power plant. Up in Cartersville, Georgia, there's the largest fossil fuel power plant in the world. They burn coal, and they'll take a train car, so like a single car on the train, which is bigger than a semi, and they will burn on a peak day in the summer for the city of Atlanta. They will burn that whole car of coal in about 5 minutes. So it's an insane amount. And what they do is they heat up water to boiling to turn it to steam, and that generates the electricity. They have to get lots and lots of water, so they pull it from a nearby river. But they have to cool it down, because if they dump hot water back in the river, less gas is now soluble in the water, and the fish don't have anything to breathe. The plants can't get their carbon dioxide. Yeah, I know my biology. And you kill everything. So they have to cool off the water to a certain amount before they're allowed to dump it back in the river. And the water just went through a cycle, got heated up to steam, generated electricity, cooled off and back. There's no chemical reactions. You just change the temperature of the water, so it's safe to dump back. But one of the things that they have to do by law is they have a little rowboat, and I know a teacher that did this for the summer, and they would get in the rowboat and they would go 2 or 3, there was a set number of miles downstream, and every certain distance they would measure the temperatures at the top, the middle, and the bottom of the river, and they had to record this every single day. And if it was getting too hot, they had to slow down the electricity production or open up another tower. They had 4 towers. So kind of neat. But the solubility curve is demonstrated, I know this looks like a mess, don't worry, okay? Is because everything on here is curved to some effect. There's a few that don't really curve much. Where's potassium chloride? That doesn't curve much. and sodium chloride doesn't curve very much. But this graph, you'll notice that we have a whole bunch of different compounds. So what I've done is the same thing as before, where I've actually just mapped out the number of grams of solute that can dissolve in a certain amount, a certain temperature of the water here. Okay? So I can read it exactly the same. We have ammonium chloride, and at 0 degrees Celsius, you can get just under 30 grams of this ammonium chloride, so a little under 30 grams dissolved in 100 grams of water. And as you heat it up, we're now at 100, so the boiling point of water, I can now dissolve about 70 or so grams of water. So in order to read this, here we've got a little fancy animation. We've got this one up here. You just look at the x-axis, the y-axis, you match them up. So at this point, remember on the line is the saturation point. This is called potassium nitrate. At that point, 50 degrees Celsius, you'll get about 88 or so grams dissolved in it. Anything above it, or in this case, kind of more to the left, is super saturated. So if I want to add more, it's above the right temperature, I've got to super saturate it. And anything over here under the line is unsaturated, and on the line is saturated. So those are the solubility curves. What you're going to do is you're going to build a curve. You're going to make some measurements, and you're going to record the temperature and the amount dissolved, and you're going to plot those on a graph. And it could be a straight line, it could be a curve, but whatever it is, we call it a solubility curve. So you're going to plot those on a graph, and as you do this process, that will allow you to go back and look at these and say, oh, this is how to read it. But they're not really all that hard to read. All right, after this, in Microsoft Teams, there is an assignment called, I forget, but it's in there, and you're going to go do that. But that assignment is in Microsoft Teams, and you're going to go do that for a summative assessment. So this one does count for a grade. Have a good day.